All right, so there were two things that I said I'd mention in a future video. The first thing is matrix-matrix multiplication. And the second thing is non-square matrices and what they represent, and also maybe just like higher dimension matrices than just the 2 by 2 ones we've been looking at. So I will start here in the higher dimension matrices. So let's talk about what a 3 by 3 matrix would represent. We talked about how a 2 by 2 matrix, right, is some like skewing of the basis vectors, and that like squishes the space. Same thing. You just add another axis, and instead of having to worry about just I and J, you now have a K direction. And again, that K direction can maybe change, and who knows what it actually looks like in space. But a 3 by 3 matrix is merely telling you where the I hat, the J hat, and the K hat basis vectors end up. And there's going to be 3 components here because the I hat, J hat, and K hat vectors end up at a different point in 3-dimensional space, because both of these axes maybe live in R3. That's kind of an easy generalization to make from the 2-dimensional case we talked about. What is a 1-dimensional case? Well, that would just be on the number line. And actually changing like a matrix, a 1-dimensional matrix that's 1 by 1, say it's like the number 3, the number line has the basis vector, though we maybe never think about it. If it's just your traditional number line, 1, 2, 3, then your basis vector, we'll just call it I hat, just goes from 0 to 1. This 1 by 1 matrix just tells you that this basis vector has now become 3. And what that essentially means for every point on the line is that you multiply every point in the line by 3. And that makes sense because multiplying by a 1 by 1 matrix is almost the same as just multiplying by a scalar. So we have the 1-dimensional case. We talked about 2-dimensional case a lot in past videos. We have the 3-dimensional case. Can't really visualize the 4 and above dimensional case, but you can imagine mathematically it's very similar. But what does it mean when you have a non-square matrix, right? In all of these cases, you have 3 basis vectors living in 3-dimensional space, right? 3 and 3, those numbers are the same. But what if those numbers are not the same? What if you have 3 basis vectors that then choose to live in 2-dimensional space? And so that's a little bit hard to think about, but let's see what that would mean. If we have 3 basis vectors, that means our input space has to be R3. That way we have our I hat, our J hat, and our K hat, right? I hat, J hat, K hat, whatever. Now what if, we've been talking about how these basis vectors like move to a different place, squish space, and that'll give us some matrix. But what if they don't just move, but they all collapse down into R2? You can imagine like maybe an XY plane's right there, and they just kind of all sandwich and they come down into 2-dimensional space instead of being in 3-dimensional space. And so now suddenly you're in R2, you still have 3 basis vectors, but they just kind of all live here now in R2, in one plane, maybe the XY, the flat XY plane. And what would a matrix for this transformation look like? You're going from 3-dimensional space to 2-dimensional space. And this right here would be, let's think about it. We have I hat, J hat, and K hat still. So it's still going to be 3 wide. But each vector now only has 2 components because they came from R3 and they collapsed down into R2. So now you're only going to have a height of 2. So this matrix right here would be a 2 by 3 matrix, not square. This representing a transformation from 3-dimensional space down to 2. So you notice that the width, the number of columns is equal to the input space, and the number of rows is equal to the output space. So you can imagine an analogy. What is a 1 by 2 matrix, for example? Well, input space of 2, output space of 1, which means our input space is like a coordinate plane, right? I hat and J hat. And you have some linear transformation that collapses it down onto a line. But you still have your basis vectors living on this line. And let's remember, let's say that we started with a point that was at 2, 1. So 2 times I hat plus J hat. After this transformation, you have these 2 basis vectors. Let's say I hat is the one pointing this way and the J hat is the one pointing this way. Where does this point end up? Well, this point ends up 2 I hats and then add a J hat, so maybe over here. But it ends up in 1-dimensional space. And you'll notice in these sorts of situations where you're going from a higher dimension to a lower dimension, you can imagine a lot of points in the two-dimensional space all collapsing down into the same point on one-dimensional space. Because there's like almost not enough room on one-dimensional space to have a different point for every point in two-dimensional space. So they have to like share. And this is really important for a concept called null space, which I don't know if we'll be able to talk about in like my videos that I make, but it'll definitely talk about it in class. And that's basically when you have a lot of different things that collapse down and become zero, right? Like a lot of different things end up just becoming zero. And you'll worry about that later. We've talked about 2 by 3, but what about 3 by 2, right? If you have a 3 by 2 matrix, what does this mean? That means your input space is 2 and your output space is in 3-dimensional space. So it's kind of backwards, right? You start out in 2-dimensional space, you just have your I hat and your j hat, and suddenly your I hat and your j hat want to break free, and they become I hat and j hat in 3-dimensional space, maybe pointing in random directions in 3-dimensional space. Now you'll notice that when you take all the points in 2-dimensional space and you have your I hat and j hat like spread out in 3-dimensional space, these points will not fill all of R3 after this transformation. Just like there wasn't enough space in R1 for all of R2 to like have their own spot, there are too many spots in R3 to be filled by R2. So when R2 goes here and you have these two basis vectors, you're actually going to end up with just a plane in R3 made up of your Cartesian plane scooting into R3. And this is similar to the ideas of span and linear independence we talked about, because with two basis vectors, you can have a span, you can only span a 2-dimensional space, right? That's almost the definition of dimension, is how many basis vectors it takes to describe. So when this R2 transformation gets turned into R3, you're going to end up with a 2-dimensional space within R3. And that can be represented by a 3 by 2 vector. And so that kind of tells us what non-square matrices represent, at least in this like linear transformation point of view. And again, also what higher dimension matrices like 4 by 4 and 5 by 5 matrices look like. So then let's move on to matrix-matrix multiplication. This is kind of scary. Oh, I did not erase the board. Let me do that. All right, so matrix-matrix multiplication. We have two matrices here that are being multiplied and then a vector, just for the sake of explanation, which you'll see why. And if any of you have seen matrix-matrix multiplication in previous classes or anything, you know it's like really complicated, and like you have to multiply this by this and this by this and this by this, like a whole bunch of rules you have to memorize. But there's a very elegant description of what's happening in terms of the linear transformation view. And that is that we know that if we take this matrix out of the equation, we just have a matrix vector product. We know that basically what we're saying is that this vector is being transformed by this matrix, where the columns of this matrix are telling us where the basis vectors end up. But what if, instead of just one transformation, you did this transformation and then you did this transformation? What would our x be? And that's basically matrix multiplication. To solve this, if you had what x was, you could multiply it by this matrix. That would give you a vector. We'll call it like x2, right? Because matrix vector multiplication gives you a vector. Then you can multiply by this matrix, and that may give you your answer. But what if you wanted a generalization? What if you wanted to know if you did this transformation and then this transformation? What if you wanted to combine that data so that you could do it to a bunch of vectors? And what you can do is matrix-matrix multiplication, which will give you another matrix that basically that combines the data from these two. And then if I use that matrix and I multiply it by x, it will tell me the combined effect of this transformation followed by this transformation, read right to left, on some vector x. And that seems like a hard thing to do, but it's not too bad, because we know that the first column here is 2, 3. That tells us where the I basis vector ends up. Then this transformation happens. What if we multiplied this matrix by this vector? We already know how to do that. That would tell us this I hat, after this transformation, if we did this matrix times this vector, it would tell us where this I hat vector finally ends up after both of these transformations. So I hat ends up at 2, 3, then it gets transformed by this, which we can do by matrix vector multiplication. Let's do that real quick. Remember, you take the dot product of this row with this column. so that'll give us 5. And this row with this column, which will give us 3. And I'll call this I2. So the I hat vector finally, after both of these, ends up at 5, 3. And we know that because we know where it ends up after the first one, by definition. Then we know where it ends up after the second one by multiplication. Similarly, we can do the same thing with the second basis vector here. We'll call it J. We know it ends up at 4, 5 after this matrix transformation. Where can we figure out where it goes after another transformation? Well, that's what matrix vector multiplication is. It tells us how the matrix affects where the vector goes. So if we do the matrix vector multiplication with 4, 5 now and this one, we should get 9 and 5. And you see that this is J2, and it tells us where the I hat and the J hat vectors end up, and it should be a generalization of applying this transformation, this squishing of space, and then this squishing of space, one after another. And that is essentially matrix multiplication. And I'm sure in class you'll learn about a bunch of like rules and shortcuts and whatnot, but that is the intuition about, or one intuition behind what it means to multiply matrices.